Hi, my name is Alan Lukajic and I will present our work Trans2k Unlocking the Power of Deep Models for Transparent Object Tracking. In visual object tracking, a tracking algorithm automatically estimates trajectory of selected object. Most of the research in this field has been focused on tracking opaque objects. These are typically well distinguishable from the background and do not change their appearance significantly through time. On the other hand, transparent objects are common in our everyday life and the ability to track them is crucial for numerous applications. Interestingly, the field of transparent object tracking is much less developed and due to the specifics of the problem, methods developed for opaque typically fail on transparent objects. Tracking is thus challenging mainly due to the background, which is visible through the object. On the other hand, they offer additional visual cues like reflections or light distortions that can simplify tracking tasks. The field of transparent object tracking has recently gained some attention since a new benchmark called TOTB has been presented. The dataset consists of 225 fully annotated videos that can be used for evaluation. The authors performed evaluation of existing trackers which were developed for opaque objects and observed that the state-of-the-art methods are based on deep learning. These methods are highly dependent on training data, but currently such a training dataset for transparent object tracking does not exist. We see this as one of the main limitations of this field and also the reason why it is so weakly developed. To address this limitation, we constructed a new training dataset for transparent object tracking, which is the main contribution of this work. When constructing the new dataset, we had to address several challenges. For example, data acquisition is a time-consuming process, especially when the dataset needs to be large. And accurate annotation of the videos is very expensive. We made several observations that were used to create the dataset. First, we observed that transparent objects can be rendered sufficiently realistically using modern rendering engines. And second, human-level realism is not required for successful training of deep models. Thus, our new training dataset is rendered, which significantly speeds up acquisition and annotation process. To demonstrate real-life applicability, the methods retrained on the new dataset are still evaluated on real videos on the recent TOTB benchmark. Now let's see how the dataset is constructed. Each training sequence is based on an existing video sequence from the Trans2k dataset. This sequence is used as a background. Then a 3D object is rendered on this video sequence. The object is selected from a predefined set of 3D models, which consists of 25 object classes and 148 instances. The object moves, rotates, and changes its size over the entire sequence. To generate new sequence, an existing engine based on Blender was used. Here is a preview of few new videos. We generate 2000 new sequences where the target is automatically annotated, thus the annotation accuracy is excellent. Per frame annotations are available as bounding boxes as well as segmentation masks. Each newly generated training sequence is parameterized by the following parameters. Transparency is defined by 4 transparency levels ranging from extreme to low transparency. Similarly, we include several levels of motion blur, rotation speed, and partial occlusion. In addition, some sequences were generated with distractors. This means that besides the tracked target, there are also some other transparent objects present in the scene. Finally, moving of the object is specified by 4 randomly selected points that form a spline in space-time. Besides translation, object also changes its size through the video and rotates around all 3 axes. When generating a new sequence, each of these attribute levels is randomly selected. The newly generated dataset is denoted as Trans2k. After creating the whole dataset, we can demonstrate its impact on tracking performance. We selected 7 existing trackers, 1 transformer-based, 2 Siamese trackers, 2 deep DCFs, one segmentation based, and finally one tracker which has been developed especially for tracking transparent objects. All these trackers were retrained using a new training set, which consists of sequences with opaque objects and with the newly generated dataset with transparent objects. The retrained versions are compared with the original trackers on the realistic videos from TOTB benchmark. Here are some quantitative results of this comparison. On the rightmost graph, we show tracking performance of the original trackers denoted by orange bars, while their retrained versions are shown in dark blue bars. We show also the absolute improvement in tracking performance on the TOTB benchmark. All methods significantly outperform their original versions and achieve up to 10% absolute improvement in tracking performance. Now let's see some qualitative examples. First, we would like to explain our decision for including both transparent and opaque objects in the new training set, which was used for retraining. Here, this is demonstrated on Siamban tracker. On the left side is a version of the tracker which is retrained on transparent and opaque objects. It nicely tracks the selected target through the whole video. On the right side is the same tracker retrained on transparent objects only. This tracker quickly jumps on the wrong object. We observe that this is a common effect when only transparent objects are used in the retraining process. The reason for such behavior is that the method gets too specialized for transparent objects, and it becomes more like a glass detector that detects the most glassy object, rather than a tracker that tracks a selected target. Here is a comparison of original DIMP tracker shown in blue and its retrained version in red. We see that the original tracker is not able to track the transparent object, while the retrained version tracks it nicely. Another example shows a Siamese tracker Siamban. The original version shown in blue quickly drifts on the background, while the retrained version shown in red successfully tracks the target. To conclude, in this talk we presented a new training dataset for transparent object tracking. The dataset is constructed by rendering transparent 3D objects on the existing video sequences. After the retraining, 7 trackers, originally developed for tracking opaque objects, were compared and achieved significant performance boosts on the real transparent object tracking benchmark. We observed several insights that were not all presented at this talk. To name a few, state-of-the-art performance is achieved by trackers based on transformer methodology. Then deep backbones outperform shallow ones. Most of the generalization for tracking on opaque objects is still preserved after retraining, and the datasets with opaque objects still need to be included in the training process. I would like to thank the co-authors of this work, and I would also like to thank you for watching.